Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to take a deeper look into the C++ Standard Template Library Vector Class, otherwise known as std::vector of type T. So I already have most of my resources set up here. I have my Visual Studio IDE. I have CPP reference open specifically to the vector class. And I also in front of me always have this guy with me, my Nikolai Jasudis C++11, the C++ Standard Library 2nd edition book. And I'm specifically open to Chapter 7, Section 3, 7.3, which is vectors. So, I mean, it gives a great definition and explanation of everything you can see. So, and there are definitely more resources out there other than just these two. So this information is everywhere. There's no paywall to find this, which is great. And so now we're ready to think about what a vector class is. So if you already know arrays, you pretty much know at least the basics of how to get started with a vector. So an array is what we call a static data structure. So that means that at compile time, we have to know how much space to allocate for the array of data that we're creating. And so if we know exactly how much data we need, that's great, and it's the fastest way to go about doing things. But in a more modern world, that doesn't really work so well, because a lot of, especially think video games or anything like that, like the amount of objects, the amount of things going on as the program is executing or the game is executing varies greatly. So if I have 100 spaces allocated for an array and I end up using only 3 of them, well, I've wasted 97 elements that I'm not using for anything. But on the other hand, if I have 100 elements set aside and I need thousands, well, I can't make that work. It's just there's too much to fit into that little tiny space. So you can see where we need a different way to go about doing things in a more modern environment. So the answer to that is to take and create a dynamic array. So, and that's what a vector is. It's something that dynamic means runtime. So as the program is executing, the vector can expand and technically retract, even though it really never does that. But it can expand to fill the role it needs to resize itself if I add too many elements, so that it's just about as big as it needs to be to get the job done. So it says the vector is a sequence container that encapsulates dynamic sized arrays, exactly that. And so just like an array, the elements are going to be stored contiguously. It's still one block of data. So we're going to see, we're going to look at iterators today. We're going to look at all sorts of other things and different ways to access the data in here. And so again, the storage is handled automatically. And because it's being handled automatically, there's more going on under the hood. So it can't be as fast as an array, but again, with all of the bells and whistles that come with this, we balance that off and say we take a little bit of a performance hit, but all of the extra busy work that goes into maintaining this vector, this array, is handled for us automatically. So let's just say, coming down here, this type T, right? Template, T for templated type. So the simplest way to set up a vector is to use something like this. And so the T type is int. In this case, I'm just going to use a vector of ints throughout this demonstration. And again, the T type can be anything: a character, short, long, float, werewolf, Cartesian coordinate, you name it. And it can also be pointers. You know, it can be whatever the T needs to be to get the job done, can be the type of elements, which is great. And so coming back, here are all the member functions that we have access to. There's a lot going on here, but I'm thinking of the constructor specifically. So this is the basic, no frills, no nonsense, just creating an empty vector with no elements inside of it. And so the other way to go about it is I can use an initializer list to say, give me a 5-sized vector, and I can actually run this, and we can mouse over the thing using the debugger. And say A, size is 0, there's nothing under the hood. All this extra stuff don't worry so much about. But B has size 5 and its elements are 1, 2, 3, 4, 5. And notice with the square brackets there that everything is exactly like you expect it to be if it was an array. So element 0 holds the 1 and so forth and so on. So a vector is a 0-based array, you know, under the hood, just like an array is, just like the true array is. So this gets me initializer list, this gets me base. What else is there? There's copy constructor. create a brand new one, a brand new vector called C using B as the template. So now if I run this one more time, then C has a completely different data structure. The elements are 1, 2, 3, 4, 5, but it's a different copy of 1, 2, 3, 4, 5. Because I don't expect to change something inside of B and also then affect the element inside of C, right? I mean, they're supposed to be completely separate data structures holding completely separate data. And so there's other ones, we'll see other ones, like here's the initializer list one, here's the move constructor we're not going to worry about, here's copy constructor. We'll deal with this in a little bit when we get to iterators. And so basically that kind of stuff. Oh, one more one we can do here is I can set up a vector and I can say I want 90 elements. And in this case, it sets them all up to be 0. And I can also set up another one and say, how about give me 15 elements and they're all starting with number 6. So we can see I mouse over D and go, there's size 90 and they all get the 0. And then I can mouse over E and go, there's 15 and they all get the 6. So that's what these two are. And everything else pretty much we've just covered by doing all of this. So it's a really complicated way to just show some pretty simple stuff. And that, again, that's why I like the Jasudis book, because it kind of cuts through all this, because this is very daunting, very scary looking at all this, the way this is written and the verbosity of everything here, and it's like it's scary. So it's like I like the Jasudis book for its simplicity. Okay, so coming back, that's basically how to get going and set up a vector, just at its basic core here. You'll never have to call the destructor explicitly. The destructor is handled whenever the vector goes out of scope, and it knows how to clean itself up and delete all the memory it's newed up under the hood, because it's dynamic, so it's newing up memory, talking with the operating system to get its job done. And so one thing here, operator equals, there's a huge difference here. It's weird in the same. If you've done this before, you know better, because these are, as much as this seems like this is identical code, C equals B, these both call completely different functions under the hood. And again, it all comes down, the question you're asking is the object, the left-hand side of this thing, is that object, does it exist in the current moment at that line of code? So because C in this moment in time is being constructed, it does not currently exist in any solid state. So because of that, it is being constructed. A copy constructor function is called to do the work. But once you get down to here and you ask that same question, you go, in this case, C and B both exist. They both have been fully constructed. This now calls this copy assignment operator, the equals operator, to do the job. And at the end of the day, the exact same stuff happens. You take everything from the right-hand side, you copy it in to everything on the left-hand side. But when it comes down to the compiler and the way that the functionality works, the way the language works, they are completely separate functions. So just so we're clear on that. Okay, so moving on. I've got, so 2 different ways to access elements, at least when it comes to like a specific element inside of here. So if I wanted to change an element inside of B, I say B of 3 equals 99. So I can access this just like I would with an array. And so let me real quickly set up a range-based for loop for every integer x that's part of B. Print x, print space. So we can start seeing this thing kind of work out here. So here is my B, and I'm gonna have to drag this over so you can see. So element 0 is a 1, element 1, element 2. So element 3 was changed from the 4 to the 99. So that worked out. Even, it's weird because it's element 3, but it's the 4th element. So there, and it prints out everything that you see there. So that's kind of what I expect. And so what happens is, what if I try to do B of 6? Because it's 5-element array. And you go, will this work? And this is the fun of programming, is it's undefined behavior, or just, that kind of thing. What will happen? In this case, there was, can I drag it over? Yep, a debug assertion failed. And this is not anything close to the same thing as an exception. This is an assertion, which cannot be, basically you cannot override this with an exception handling case, a try-catch block or anything. So all I did was go outside the bounds one little tiny bit, and I've crashed my entire program. So if I want to do something like this and be able to find my way and say, oh, there was an error and work my way out of it, I have to use the at function. And so this will crash. Like, Brad, what are you talking about? This will crash, but notice it crashed in a completely different way this time. Instead of an assertion that came up that we can't get, we cannot get around, now we have an exception that was thrown that was unhandled, which that actually is something we can handle with a try-catch block. Come on, formatting. Okay, try, catch, and then this would be STD exception. So this can, well, if I do the syntax right, it's recoverable. And there's my oopsie before I do all the work. It prints oops, or whatever I need to do if that error pops up in my program. But just, you can silently fail, you could print something, you could halt the program, whatever needs to occur. That's on you as the developer. But again, I can't, with just using square brackets, there's no range checking, and in this case, the size of the thing was 5 and the capacity was 5, so I actually stepped completely outside of the vector, and that's why the operating system just had none of it. But in this case, the at function will throw an exception, and I can handle it. So, as much as we love to use the square brackets, the at function is probably a better way to go about doing things. So I have also access to the front and the back. So like, and for a vector, like I want to see the first element, I want to see the last element. So what's interesting is this actually returns a reference. So this is where programming becomes interesting and fun. So I can let me get rid of this just for the time being, since we don't necessarily have to have this. But coming back to my B example, what if I say int reference, just P equals B of 1. And then I go P equals 86. Or how about this case, instead of B of 1, how about I just do B dot front? And so yeah, that's what I'm trying to do, right? Sorry about that. It's hard to remember these things making these videos sometimes. But okay, so I'm going to get the front element. I'm going to put it into B as a reference, set P to 86, and then print everything out. And well, lo and behold, what do you get here? Oh my goodness, the 86 is actually changed. And that's, again, this is the difference between a value type and a reference type, or a pointer type, if you want to think of it, since references and pointers are almost the same thing, with a few key exceptions. But what's happening is, since this function returns a reference, it's returning a memory address to the first element of B. So it's returning that memory address. So if I go, and so what the reference means, it's a memory address. So when I go P equals 86, this basically says, oh, I know I'm a reference. Go to that memory address and change the value to 86. And that's why it prints out 86, 2, 3, 4, and 5, even though we never explicitly changed any part of B directly, right? It's part of P, which just happens to be the front. And the fun part of this is, what happens now if I just remove that little ampersand? And now that one little ampersand changes everything, so that now it prints 1, 2, 3, 4, 5 instead. And you go, what in the heck? And that's because even though this is returning a reference, the integer data type does not hold a reference, it holds a value. So the programming language goes automatically to that reference, gets the value stored there, and makes a copy of it and puts it into P. So a completely different data structure, a value type, an integer, versus a reference type, int reference. So in this case, I'm changing 86, which is a completely separate copy of the 1 that is the first element, and so it's not modifying B directly. And so this just comes down to a huge difference between what value types are and reference and pointer types are. Copies of data versus the real deal data. And I like to use the Xerox copy example when it comes to value types, and then that kind of thing when it comes to that. So front and back, those are, you can get access exactly the same thing. If I want to do the same thing for the last element and change the last element to 86. 1, 2, 3, 4, 86. And again, these functions presume there is a first last element. So if I do this on an empty vector, I'm going to have a crash. Alrighty, so let's see, we'll come back to iterators after we do capacity stuff. So pretty simple stuff. Empty if a.empty equals true, cout empty. And will it do that? Of course it will, because A is empty. There's my empty. And that means a size of 0, of course. And so, of course, if I do B has 5 elements, it won't print empty because it's not empty. So so that is how much, that's as much as you need to worry about that. So when it comes to this, you can do size. If B of size equals 5, something like that. And you better believe that works out because the B has has 5 elements, and the same thing goes if does B have 0 size? No, so it doesn't print. So I mean it works exactly like you expect it to for the number of elements. And so one big thing here, like when it comes to a vector class, is there's a difference between the size and the capacity. So let me see, and let's say we haven't talked about pushback or anything like that. Let me see. Let's just take a look here. When I run my program, let me hit a breakpoint here. And I say B size of 5, and then you can see capacity of 5. And that's that's an attribute sitting under the hood. And so what that means is that, if you've ever heard of a partially filled array, and you've ever done that example, depends on the class or the instructors you might have had in the past. And I go, well, there's a completely different thing about basically capacity versus size. Think of maybe an egg carton. And so when you buy eggs at the store, you have 12 eggs. Your size is 12 and your capacity is 12. But as you start using the eggs, the number of eggs you have, the size of your eggs is reduced, but the capacity stays the same. The carton of eggs never gets smaller. It stays as a capacity of 12 as you reduce the number of eggs down from 12 to 0 before you do whatever you're going to do with the egg carton. So the same thing applies here. But we do it the reverse. We generally take an empty egg carton and we start adding eggs. And then when we need more space, we find a bigger carton and move everything over. So that's essentially what's going on here. So the capacity is a way to tell me how many elements could be stored under the hood before I have to worry about finding a bigger space for the number of elements inside of my vector. And so I can reserve space. And so like if you know you're going to have like a deck of cards or something like that, I can say, let's reserve me 52 spaces. And so previously here, I can do I can run this again. Come on, guys. Run this again. And I go A, size of 0, capacity of 0. But then under the hood here, when I do a reserved 52 spaces, there's still 0 elements here. But if I go to try to add anything else, I add stuff, it knows to basically set aside 52 elements to start with. Instead of setting it up with 1 or 2 or 5 or whatever the number of elements, it generally starts by default. And so again, because this is dynamic size and everything is being handled under the hood, you want to keep the number of copies you make as little as possible. So the reason why I want to reserve 52 is because just think about, talking about the egg example. If I have, I'd start with an egg carton with 12 capacity and I add eggs, and then when I hit 12 and then I want a 13th one, well, I got to go find a bigger egg carton. So I find a bigger egg carton, then I move all the eggs from the little one into the big one, and then I can add the 13th one, and then I can keep going. But what happens if I fill that one and I still need to move on? Well, I need to find a bigger space for those eggs and then move all the eggs from the second carton into the third. And so this might happen 5 or 6 or 10 times depending on how many elements you're adding or how many eggs you're adding to your carton. But what if you just said, oh, I know I have 1,000 eggs. Why don't I find 1,000 sized egg carton so I don't have to do all that extra work and I can just do it one time and move the egg into the carton. And it's the same idea here. You're saving the processing a ton of time of having to make an array, put stuff in, and just to copy it into a larger space, and then just take that and copy it into an even larger space, and so forth and so on until you finally get to the finality of what you're trying to do with the size you have. So that's the concept here, and it's very easy because so much of C++ and so much of general programming is, if you don't know these little tiny details, your program could very much suffer performance penalties because nobody told you, or it's just presumed you know these little details. Okay, So moving on to iterator types. So cool. So iterator types. So there's one final way that I can generate, let's just say, let me change this up. One final way, instead of using a range-based for loop, why don't I use iterators to go through, iterate through the entire vector instead of doing things this way and just print out all the elements. So I can start out and I can get an iterator. Iterator is a subclass. And I can say iterator iter equals, and I can say b.begin. So that's this guy here, the begin iterator. And so that will get me, essentially, it's not the same. An iterator is not a pointer, but it's a class that kind of behaves as a pointer, if you want to think of it that way. It's like, get me the first element. Get me the first element of my vector. And now I can change this into a while loop, and I can say, while my iter does not equal b.end. And so end is another iterator, and surprisingly enough, that's actually one past the end, like, because I need to access 1, 2, 3, 4, and 5. And so because of that, the end iterator is actually one past the 5. And you're like, well, doesn't that make, didn't you tell me I can't go past the array bounds? And I go, yes, but you can't access past the array bounds. But if you go to the memory address or something one past it, it's fine as long as you don't try to access the data at that location. Because at the end of the day, a reference, a pointer, is just a number under the hood. So if whatever the element past the 5 is, whatever memory address that is, as long as you go, hey, did I reach that spot yet? Everything's going to work out fine as long as you don't do it like we did earlier. Get me the 6th element. That one crashed horribly. But if you're just checking, is this the 6th element? And it says, yes, you are. And then you go, okay. And then everything's okay. And you don't have to worry because you didn't try to go into memory you weren't supposed to go to. So while my iter does not equal b.end, print out iter. And you're like, oh, that doesn't work because iter, this iter type is an iterator, and you have to use the dereference operator in order to go under the hood and go, get me the data stored inside of this class. So this just returns the t type, which just returns the int. And so I still forgot something, so let me run this, and you can see what I forgot. Oops, let me start over. And so, oops, all these breakpoints, boink, boink. And then, yes, because this is the difference between using different data structures and range-based for loops and whatnot. Like, haha, it's printing 1 forever because it's printing, I'm at the begin iterator, and I said, print the begin, and then while I'm not at the end, but I'm never changing access to get to the next step. So I do plus iter, and now I'll get 1, 2, 3, 4, 5, or whatever, 1, 2, 3, 4, 86, or whatever it is that I have from previous examples. Okay, so that's how you use begin and end, and a lot of times we actually use cbegin because in this case I'm not modifying anything, right? I'm not changing. I'm just using this as a read-only type of deal. So I can change this into a constant iterator instead of just a plain old iterator. So this way I can't go ahead and try to change the value stored under the hood. This will come up with an error because I'm not allowed, oops, sorry. Expression must be a modifiable L value, and it can't be because this is a const iterator, which is very specifically saying I cannot modify. So now, same deal, prints the same deal, and again, const is this thing in C++, it's like a cult kind of thing where you can go fully down the rabbit hole of const, and if you've seen, like I try to stay away from that. And so that's C++ a lot of times, and it depends on who writes the code. But you'll notice, like, you take this const to an extreme on one end, the way C++ does things, and then on the other side of things, you get, like with what you call Python language, programming language, there's no keyword const at all. So like my goodness, right? One balance to the other. And so the modern world pushes more toward no constness whatsoever. But just understand the constness is there to try to help you and your fellow programmers to make sure you don't make mistakes to change data you're not supposed to be changing. So just the old way versus the new way of doing things. So just to show that it is possible. And then this also shows that I can actually do reversals of iterators. So if I want to print, let's see, is it const reverse or reverse const? I'm going to const reverse. There it goes, it changed on me. So CR begin, const reverse iterator, CR begin, plus plus this to that. And now it's interesting, right? Because now it goes in reverse order, 86, 4, 3, 2, and 1. And you're freaking out maybe because you see plus plus iter, but it's because this time I'm starting at the back, and now when I actually increment the iterator, it's actually moving forward. That's why it's plus plus, but by moving forward, it's moving backwards. And we're having like a Willy Wonka moment here where you're like, you know, we gotta go frontwards and backwards and sideways and long ways, but it's really, it's going forward in its own right, like stage left versus stage right. By it going plus plus, it's actually going forward, but because it's a reverse iterator, forward is backwards. So this is perfectly legit too. So that's why there's 8 different iterators, because you have 2 different things, or 8 different iterators, 4 different ways you could set this up, and the two questions are: do I want to go in reverse order, or do I want to be const or not? So that's how you get 4 different ways to access and iterate through, and then you need 2 iterators for the begin and the end. Okay, so that handles the idea of iterators. Oh yes, and last point here, using iterator types, is I can use iterators as part of a constructor. So I can set up F, I guess. Do I have F? No, I think I'm good with F. And I can say, and then inside of here, I can say, give me b.begin and b.end. And so this is a completely separate way here of setting up. And so let me change this down here so I can use F instead of B to print out everything, just to show. And I can print out, there's 5, 4, 3, 2, 1, because I took B right here, I created it, and then I immediately copied, and I started from the begin operator, or begin iterator, and went to the end operator and copied it all in, and then I printed it out in reverse const order. And so what's cool about these iterators, at least when it comes to vectors, is if I wanted to, I could do something like this, where I can actually take the iterator and say, hey, move one over, one way or the other. And so if I run this one more time, get rid of this thing. And so now you can see here, I can go, okay, take begin and move over 1. So basically skip over the first element, don't copy that in. And the same goes for end, don't copy the 1 over. So that's why instead of it being 5, 4, 3, 2, 1, when I print this out here, you see it's 4, 3, 2, because it eliminated both the 1 and the 5 from the list. So it's a 3-sized vector. And if I do this in reverse order, it's 4, 3, 2. So this only works with these kind of data structures like the double-ended queue and the vector. This doesn't work for lists and sets and maps and those kind of things. And that's a lecture for another time. Okay, so that is the final important constructor to worry about, is how to set things up using iterators. So now all of these other functions, for the most part, not all of them, but most of them require the use of iterators to do their job. So let's just say down here, okay, right here, just we know it's been printing out whatever it's been printing out. What if I do f.clear? Clear means exactly what you think it will. It just sets the size to 0. And so now, and eliminate everything under the hood. So if I do that, it doesn't print anything because f has been cleared out. Even though there was 3 elements in there a second ago, I was like, nope, now there's 0. There's nothing to print. So that does exactly what you're thinking of. But you have to always worry when you have pointers to things, especially if you were the one that newed up the memory. If I just do clear, it doesn't do any of the deletions of any of the pointers sitting under the hood. So if you do clear and you don't do a delete, you have a memory leak. And memory leaks are never good, never, ever, ever good. So just watch out for that. Okay, so the one thing we have never done here is we've never gone ahead and let me get rid of the clear so we can get, I've never actually added to the size of this thing. And so, because I mean, we've basically been treating this thing like an array the entire time, but that's what the pushback function is for. So pushback does exactly what it sounds like. It takes and puts an element at the back of the list. So if I want to put 77 in here and print everything out, and printing it in, and so let me get rid of the reverseness. I don't want to confuse anybody here. Let me just get rid of this reverseness and just make this C begin and C end. Okay, let me just print this out here. So then now 2, 3, 4, 77. So I pushed the 77 to the back of this thing. So 2, 3, and 4 were the elements we were just talking about, and then 77 gets added to it at the back. And there's no way to push to the front. A vector is not like a double-ended queue or anything like that. The only way you can push elements is to the back, and that's, this thing is front-loaded, and we'll see for other examples too, that if you want to push to the front or add to the front of this thing, this is not the data structure for you. Or if you want to insert or remove elements from the middle or the front, the vector is not your class, is not your data structure. So push back, and then you could do a pop back. So we just showed this, so it eliminates the final term. So then now we're right back to where we were. The 77 gets pushed on, and then the 77 gets popped off. So if I really, so coming down here, I could do this, put this inside of a while loop, while f dot empty equals false. Print all the elements, and then let's print an end line. And then why don't we go ahead and then f dot pop back. So what does this do? Check it, think it out, think about it, pause it if you have to. But what this does then is it prints out this, while this thing is not empty, it'll print out every element using this crazy iterator method, and then it'll print an end line, which goes to the next line, and then it'll pop off the final element. So that's why it goes from 2, 3, 4 down to 2, 3, because the 4 got popped off, does it again, and then brings it down to 2, and then when it pops off the 2, the thing is empty, so there's nothing left to do. So that's kind of how you could go through. And what's nice about this is you don't have to worry about starting with a 5 size or anything like that. It just, no matter what the thing is, it will work its way down one element at a time using popback. Okay, so then the final things to really worry about here, the only two I'm going to talk about then, is insert and erase. So again, what's coming back here is I need an iterator to make this thing work. So I can change this up here. Instead of doing f.popback, if I want to do an erase, and say now instead of erasing that popped off the back, what if I wanted to pop off the front? So what I could do is say f.erase, and I could say f.begin, because it's an iterator that's needed here, right? So because let's see if I can look in here, and it says, okay, it needs an iterator of some sort to erase. So it says, okay, get me the first element, get me the access the iterator to the first element, and erase that. So now you can see now it's 2, 3, 4 just like before, but if I'm erasing the first element each time, then it's going to do 3, 4, then 4, and then kick out on here. And you're like, why doesn't it include, why isn't it like an index value? Why isn't it an iterator? And that's just because, again, this is a standard library, and this is about the only data type we could access and say, just erase the 9th element, and it would actually work. And because it's just the way that, because it's one contiguous block of memory, it can actually handle that. But other data structures, memory is kind of spread all over your CPU, or not CPU, all over your RAM, and so in that case, it doesn't get to do that kind of stuff. So what's happening, again, because this is a vector, not another data structure, is what's actually happening is when you erase an element, in this case the first element, it's basically taking all the other elements and copying them over. So this is, especially from the front, if you have a 10,000 element array or something like that, and I want to eliminate the first element, well, what I'm doing is copying 9,999 elements over to technically erase that first element. And so again, that's terrible compared to like a double-ended queue where the data structure can handle that much easier because it's a little more complex under the hood, but it accounts for that, and it's a very simple operation to pop from the front. But this is not the same case. So erase goes ahead and does that. So erase again copies everything over. So again, it can be a very expensive operation. If you're near, that's why everything pushes when you do a push. That's why it goes to the back, because if you push to the back, you're never worrying about any of the details about what happens. You're just putting it as the final element. Nothing else has to be shifted around. But if I wanted to push to the front, and like that's with an insert here, if I wanted to insert in the front, I can go insert, and I go, okay, I can insert. I want to insert. Let's take a look at what the functionality here. I tell it where and then what value. So I can say at the beginning, put in a 44. And so there is my 44, and F begin is basically at the start, before the element, put a 44 in there. So then the 44 went before the 2, the 3, and the 4. But just the same idea here a minute ago as the erase, what that means is it takes all the elements and shifts them over. And so in this case, again, it can be very expensive to do that if you have a huge vector, huge vector, and you want to add something that isn't at the back. Everything else from that point on has to get shifted over to accommodate. So if you continued to push to the front, it would get more and more daunting. It would take more and more processing every single time. And that's, again, why if you need to do that, the vector is not the data structure for you. So let's see. So that, I mean, outside of that, I mean, there are still details that I have not covered in here, which is all the in-place stuff is not something that needs to be introduced at this introductory level, but we've pretty much covered every other detail when it comes to setting the vector class up. So I'm glad I got a chance to make this video to kind of clear up and have a video example for especially you guys, my students, that you can fall back on something and see kind of how things work. It's outside of a book environment. So as always, if you have any questions about any of the stuff you've seen, or oh my God, have I made a mistake? It's very possible I've said the wrong thing accidentally. It's been a 36-minute video here. Send me a comment through YouTube here. Send me an email through the school. Get a hold of me some way. Ask your question, and I'll get back to you and answer as best as I can. Thanks for sticking this out with me, and hope to see you in another video. Take care, and have a good one.